All right, ladies and gentlemen, boys and girls, we are finally going to conclude the marathon 4.1, looking at some antiderivatives of trig functions, and then finally looking at finding a particular solution to an antiderivative. Okay. So I know this has been a bit of a long slog, but we are finally coming to the end. And so let me share my screen. What we'd seen previously was first just introducing the idea of the antiderivative, and then we worked through some theorems that allowed us to tackle polynomial functions and any power function, and turning some situations that were not initially those things into situations where we could apply those power theorems. And so today we're going to look at the trig functions, and that'll kind of be the last of our sort of basic antidifferentiation theorems. And then in 4.2, we'll pick up and look at some different techniques when you can't just, when it's not just polynomial or a trig function. Okay, I'm just going to throw the trig theorems at you. The proofs are basically just differentiating the right side. Okay, so if you want to do that on your own to prove to yourself, but these are just kind of, they follow directly from the trig derivative theorems. Okay, so we'll call these the trig theorems. Which in reality are 4.1.9 to 4.1.14 in your book. Starting with the antiderivative of the sine, well, let's think about this. Oh, sorry. What, when we differentiate it, gives us sine? Well, right off the bat, it's kind of a curveball. Nothing, well, not nothing. We don't have a trig theorem that gives us sine. We do have one that gives us negative sine when we differentiate. We know that the derivative of the cosine is the opposite of sine. And so going the other way, the thing that will give us sine as its derivative is negative cosine of x plus c. Quick check in our lines. If we differentiate negative cosine of x, the derivative of the cosine is the opposite of sine, and the opposite of the opposite gives us just sine. Derivative of c is 0. It checks out. Okay. Moving right along, if we want the antiderivative of the cosine, well, for that one, we do have a trig derivative that gives us the cosine. It's the sine. And so the antiderivative of the cosine is sine of x plus c. For the antiderivative of the tangent of x, I'm sorry, of the, oh yeah, so these are kind of, yeah, so we actually don't have tangent. We have, oh, sorry, I know I keep using the no sleep excuse, but it's true. So I do have a iced coffee with horchata though, which is as delightful as it sounds. Little 4 p.m. pick me up. Time has no meaning when you have a week-old child. It's just a flat circle that is meaningless. And you sleep when you can, which is never. But parenting is awesome. Okay, where was I? Saying that we're not going to look at the tangent because we don't have a trig derivative that gives us a tangent. Okay, when we differentiate the tangent, we get something, and so that's kind of how we're going to do this. So when you differentiate the tangent, you get the secant squared. So secant squared secant squared's antiderivative is the tangent plus c. Okay. So then kind of working that same backwards thought process. And actually, let's even just do it that way. We know the cotangent of x gives us the negative cosecant squared. But we don't really want to put negatives in here, so the cosecant squared will go in here, and then we'll put the negative out here. So the antiderivative of the cosecant squared is the opposite of cotangent plus c. Kind of playing the same game again with the secant. The derivative of the secant is the secant tangent. And so the antiderivative of secant tangent is secant plus c. And then last one, the cosecant. It's going to be a similar outcome as the cotangent, where when you differentiate the cosecant, you get the opposite. You get a negative result, the negative cosecant cotangent. So we're going to turn that into the positive cosecant cotangent and start out with this negative. So the antiderivative of cosecant cotangent is the opposite of cosecant plus c. Okay, and so basically the game that we're going to play in some of these examples is just seeing if we can identify these 6 expressions who have easy antiderivatives. Okay, and then the other game that we'll do at least one example. Actually, we're going to do 3 trig examples, kind of like an easy, medium, hard, and we'll see how they progress. But there is a table on page 321 with some common trig identities that will probably help us as we move through these. And none of them are psycho, like they're all pretty straightforward. It's none like double angle theorem or anything like that, just sort of some trig identities. Okay, so we're going to start out with an easy trig, and this is example 4. Easy, medium, hard. Example 4. If we want the antiderivative of 3 times secant x tangent x minus 5 times cosecant squared x, we can do that. We'll kind of like hunt through this and see, okay, do we see, okay, there's one, and there's one, okay, we can do this. Easy meaning the expressions involved from the get-go are the left side of one of these 6 theorems. Okay. And I will kind of break this down just a little bit smoothly and nicely, just so you can see that, okay, this is going to be 3 times the antiderivative of the secant tangent minus 5 times the antiderivative of the cosecant. Oh, sorry, there's a dx in here. There's a dx, can't forget the dx. Cosecant squared dx. And now, okay, that's the left side of this guy. That's the left side of this guy. And so this turns into 3 times the secant of x minus 5 times the opposite of the cotangent of x. And then we'll just do one generic c. You don't have to do a separate c for each guy. And then just simplifying this, we get the antiderivative is 3 times the secant of x. I get nervous every time I'm writing secant of x that it's going to turn into that, and it just happens. So, whoops, secant of x plus 5 cotangent of x plus c. Okay, so not that bad. Easy trig. Let's see a medium trig. Which corresponds with example 5 in your book. Example 5 is the antiderivative of twice cotangent minus 3 sine squared divided by sine. And that's all dx. So medium trig is going to probably require us to do at least some sort of rearranging or application of some basic trig identities. And so for this one, the first thing we're going to do is just actually break this apart and actually do this division. And so this will turn into the antiderivative of twice cotangent x times 1 over sine of x. This is, I'm going to break this apart, yeah, sure, minus 3 times sine of x. All I did was just divided this guy by sine of x and this guy by sine of x. Okay. Okay. So now we can rewrite this as 2 times the antiderivative of cotangent x. Well, 1 over sine is just the cosecant. So easy trig identity. 1 over sine is cosecant minus 3 times the antiderivative of, and I keep forgetting the dx, sine of x dx. So now we have transformed this into something where we can find both of these expressions on the left side here and evaluate. So the antiderivative of the cotangent times the cosecant is the opposite of cosecant. The antiderivative of the sine is negative cosine, and all plus c. And so then our final answer is negative 2 times the cosecant of x plus 3 times the cosine of x plus c. And you really should take a second, maybe press pause and differentiate this and make sure, no, that gets tricky. Never mind. Forget I said that. I guess you could. That's fine. We're okay. Okay, and now finally the hard trig. We'll be okay now. And this is example 6, maybe? Sure. Example 6 is the antiderivative of tangent squared x plus cotangent squared x plus 4. Oh yeah, this one's fun. This one's cool. This one's cool. And we're looking at this and we're like, oh man, there's nothing up in those 6 theorems that involves a tangent squared or a cotangent squared. What are we going to do? Well, what we're going to do is, if we're truly blanking, listen to what I said and go to page 321 and look at those trig identities. And we're like, that doesn't look very helpful, 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 that doesn't look, oh, these look helpful, these look helpful. We can turn these into secant squareds and cosecant squareds. How? I'm just rearranging. Okay, we're going to write this as the tangent squared plus 1 plus the cotangent squared plus 1. Where are these 1's coming from, Mr. Smith? Well, we had this very handy 4 here, and we can break that 4 into however many pieces we need. We just took 2 of them, and so we still have a 2 remaining. So I'm just rewriting 4 as 1 plus 1 plus 2. How does this help us? Well, because now we can rewrite this as the secant squared and this as the cosecant squared. And isn't that helpful? I don't know, maybe. This is the integral of secant squared plus the integral of the cosecant squared plus the integral of 2. Now we're in business, because now we do see a secant squared and a cosecant squared. Now this is back to the easy problem. Okay, so the idea is like these hard ones, eventually we can rearrange and reduce and rewrite so that it becomes an easy problem. This is now an easy problem. This is just applying verbatim theorems from the top of the page. And so the antiderivative of the secant squared is, of course, the tangent. The antiderivative of the cosecant squared is the negative cotangent. The antiderivative of 2 is 2x's. And then never forgetting to add our c. That would have been such a tragedy to do all that good calculus, all that good trigonometry, and then forget the c, and then be a sad panda. We don't want sad pandas. So trig stuff, you know, everybody's favorite. So we're gonna finish up with 2 last examples where we're gonna get rid of this c, or not get rid of it. Yeah, we're gonna solve for this c given specific parameters. Okay, because again, the idea with the antiderivative is that a given function like tangent squared x plus cotangent squared x plus 4 can have a multitude of antiderivatives because there are multiple functions whose derivative is this thing that we started out with. Now, they're not wildly different. They all have tangent x minus cotangent x plus 2x, and then they can be different by some constant c. So this is our general antiderivative. But oftentimes we will be asked or interested in knowing a specific antiderivative given a specific boundary or initial condition to a problem. And so we're going to look at 2 examples of what that could look like and how we could solve for C. So this will be illustration 6. And there will be kind of a brief sidebar in illustration 6 where we will maybe not totally not to full satisfaction explain the dx situation, but we will start to shed some light on why do those anti-differentiation expressions have that dx hanging on the end. And this illustration, I think, will help to show this in a way that if I had tried to explain it before, it might not have been totally satisfying. But now that we've done some anti-differentiation, I think this will maybe grab hold a little bit easier. And so I'm going to set up the problem first and then show this process of kind of separating those parts of our derivative. So what example 6, or I guess this is illustration 6, wants from us is a particular solution given, we can call them initial conditions or boundary conditions. Okay. And so what we're given is that we have some equation. We don't know what it is, but we know what its derivative is. dy dx. The derivative of y with respect to x is 2x. And so what we could have done so far is just say, okay, well, the antiderivative of 2x is x squared. Okay? But we're going to do a little bit better than that, because now we're going to be also told that when y is going to equal 6 when x equals 2. So these are our initial conditions. Okay. Okay, so here is now where we're going to kind of start to maybe think about these separate dy and dx. So we have not done this before. We've always treated this as just an inseparable net, that this is the derivative of y with respect to x. But it's also a ratio of two different things, okay? This vinculum here, this fraction bar, generally notates a fraction or a quotient or a division process. That dy is literally being divided by dx. What the heck are dy and dx? We're not going to get super hung up on what they are, but you just need to be okay with the fact that this is an actual ratio that we can separate. And so instead of saying that the derivative of y with respect to x is 2x, this can be rewritten as dy, whatever dy is, and again, we're not worrying too much about that, is equal to 2x times dx. Where are you going with this, Mr. Smith? Well, where I'm going with this is that we want the antiderivative of 2x. So let's apply that operation, that integral symbol, to both sides. So this side looks familiar. This is like what we've been doing. And let's actually just do this. The antiderivative of 2x is going to be x squared plus c. Just quick check in our brain, we differentiate, it becomes 2x. Let's consider the left side. What is the antiderivative of dy? It's really just the antiderivative of 1. But now with this y, this is a direct application of that theorem that we saw. I'm just going to point to it. This guy. It just becomes, well, in this case, it was x. So it kind of stands to reason that if this is a dy, this antiderivative is just y. And so where the dx comes from is through this unshown step up to this point of separating out the derivative and the two parts of it that are called differentials. We just haven't really been explicitly showing that. But that's why this dx, and sometimes it's a dt, or sometimes it's a dr, whatever it is. It comes from this starting point that when we're finding the antiderivative, we're starting with a derivative. The derivative of something, of some function, is 2x. And so we can say that dy dx is 2x. We have that separation. We take the antiderivative, and we end up with this general solution here, that y is equal to x squared plus c. Okay. So this is our general solution. And this is where we've been stopping because that's all we could do. But now we are given these initial conditions that will allow us to find the particular value of c in this situation. And so what we're told is that y is equal to 6 when x is equal to 2. So plugging in 6 for y and 2 for x will allow us to solve for that specific value of c. Okay, so specific means we're going to use initial conditions. And the initial condition was that y is equal to 6 when x is equal to 2. So c is equal to 2. And so our specific solution, or particular solution is sometimes called, is y is equal to x squared plus 2. Specific slash particular solution. Cool. Cool. Okay, and then final example. And this is actually a full-fledged example, example 8. Same idea. We're going to be given a derivative and some initial conditions, and we're going to want to find the specific or particular antiderivative. So we have a derivative. Actually, the way it's worded is that at any point x comma y on a particular curve, the tangent line has a slope equal to 4x minus 5. If the curve contains 0.37, find its equation. Okay? So they've given us the derivative without calling it the derivative. They give us the slope of the tangent line, but that is the literal definition, or one of them, of the derivative, the slope of the tangent. Okay, so the derivative in this function is that 4x minus 5 expression, and the curve contains the point (3, 7). Okay, so we want to find the equation of a curve whose derivative is 4x minus 5 and contains the point 37. So we don't know what the equation is, but we do know its derivative. Okay, and so we can use this process of antidifferentiation to find the antiderivative, the equation who generates this derivative, and then, because it's going to have that arbitrary c in there in this family of functions, but because we now have this initial condition, we'll actually be able to find the particular equation that yields this derivative and contains this point. Okay, so very similar to our illustration 6, the derivative means that dy dx is equal to 4x minus 5. Separating this out, we get that dy is equal to 4x minus 5 times dx. Applying the antiderivative, the integral to both sides, that antiderivative becomes y. Over here we get are we going to show this step by step? No, we're going to start to be savvy. If the derivative of something is 4x, then that thing is probably 2x squared. Quick check. That becomes a 4x. And then this is minus 5x plus c. So any equation of this form where c is some constant will give us a derivative of 4x minus 5. So this is the general solution, the general family of curves whose derivative is 4x minus 5. But there is but one equation of this form that contains the point 3, 7. And so now we can use those conditions to find that. Okay, so use initial conditions. That's not until that. Conditions. Okay, this is given to us in a slightly different form than we saw up here. Up here, they just said, okay, when x equals 2, y equals 6. Well, here we have a point. So y equals 7 when x equals 3. So plugging in 7 for y and 3 for x. So 7 is equal to 2 times 3 squared minus 5 times 3, and then solving for that c. So we get 7 is equal to 3 squared is 9, 18 minus 15 plus c. So c is equal to not 10, 3, 4. Somebody help me. 18 minus 15 is 3, subtracting 3, yeah. C is equal to 4. Holy moly. So our particular solution is that y is equal to 2x squared minus 5x plus 4. Particular solution. Okay, so that was a marathon. Do I know what your assignment is for this bad boy? Let me see. Give me a sec. You know what? I'll post it to Canvas. I don't have the assignment sheet right in front of me. So that's 4.1. I know that was a lot. We did it. And we'll also do 4.2 this week. So it's going to be a bit of a slog this week, but we can do it. All right. I will hopefully see you guys soon.